Okay, so the last thing I'm going to tell you about, and this is kind of a natural segue into the lecture on machine learning for fluid mechanics. Oh no, what happened? There you go. In physical systems, in systems where we're going to put this technology on aircraft and in cars, we need our models to be interpretable and generalizable. Now, I struggled with this. Should I try to define interpretable and generalizable? In fact, I am almost certainly using this in not the way that a machine learning or statistician expert would use this, and I am not going to apologize for that, because these words mean something to us, and we had these words first. You know when a model is interpretable and generalizable when you see it. So the example I like to give is Newton's law, F equals ma. So F equals ma is the quintessential model that is interpretable and generalizable. It only has a few terms, and you can learn it from an apple falling on Earth, and you can use it to put people on the moon. Okay, that is generalization at work. Okay, you didn't have to you didn't have to collect data from failed missions to use F equals ma to land people on the moon. Okay, so a great quote from Einstein: everything should be made as simple as possible, but not simpler. That, again, that goes to our principle of parsimony that we talked about the other day. You fundamentally want the simplest model, not just the one that has the 0.1% better error, right? That's not for us. Oftentimes, we're going to promote these models with sparse models, low-dimensional models, and robust statistics. So that matters a lot for fluid mechanics. And what I'm going to do next is I'm going to talk a little bit just about trying to understand modern machine learning advances in the context of historical scientific discovery. Okay, I think this is really fascinating. I know a lot of us are interested in the history of science, and kind of, you know, it's very exciting, all of these great discoveries, triumphs of humankind. And we can learn a lot by just asking ourselves the question, what would happen if we gave the data that Kepler had to a machine learning algorithm? Things like that. Okay, so we're going to work through some thought experiments of classical discovery contrasted with modern data-intensive discovery. Okay, and there's going to be three pieces. So we're going to start with the Ptolemaic system. So Ptolemy was a Roman astronomer who created this extremely accurate model of planetary motion and the motion of the stars. So if you think about it, right, our planets are named after gods, right? Because they're the only objects in the sky that had free agency. Everything else has a very prescribed path across the night sky, but the planets are strange. They have agency. They do whatever the hell they feel like. Sometimes they turn around. They didn't decide they don't want to go that way. And so understanding where planets came from and are going and what they are, I mean, this has fascinated people forever. Okay. Actually, I was talking about this with my kids. If you think about astrology, so astrology is a great example of overfitting. Seriously, you know, 10,000 years ago, astrology was extremely useful. When do you plant your crops? You use the moon, you use the stars, right? That's astrology. Had a very real use in the development of human civilization. And then we just kept fitting it and fitting it and fitting it. And now people have kids at particular times of the year because that's what the stars tell you should do. Okay, so that's kind of overfitting. The Ptolemaic system, this is a beautiful armillary sphere in Florence. I would recommend everyone check this out. This is Sartucci's armillary sphere. It's absolutely beautiful. And it has this, you know, 7-layer model of existence of, you know, the solar system and the planets. And the idea here is that with the Ptolemaic system, you could model the motion of the planets as circles on circles. So you would take a big circle, and then you'd add a little circle, and then you'd add a little circle, and if you added those all up, you would get the motion of the planets. Okay, does that sound familiar? Sounds like a Fourier transform. Okay, this is basically a crude Fourier transform. extremely accurate. There's a reason it took 1,500 years to knock down the Ptolemaic system. It's because it was actually more accurate than Kepler's model. Kepler could not make a model that was more accurate than the circles on circles until like kind of the very end of his trials with this. Anyone remember where this is from? Just pop quiz for... No Jim Henson fans? This is from the Dark Crystal. This is a model of their universe. So this is a great video from 3 Blue, 1 Brown. I don't know if any of you follow this, but I would strongly recommend it. This is kind of illustrating this Fourier series of circles on circles on circles. This is showing you that you can just take your astronomical data and fit it using circles. But this was not a physics model. This was a descriptive model of the data. Okay, this is what machine learning would do. They would give you the Ptolemaic system. But it would not tell you that fundamentally there are objects called ellipses, and it would certainly not tell you that F equals ma is the reason we have ellipses. This one's great. Fourier transforming Fourier. And you can see how many circles on circles and circles. I mean, if you have enough, you can fit this, right? Okay, so I think that's pretty interesting. There's another parallel that has been we've been thinking about recently. This is work with Brian De Silva and Nathan Kutz. Is this view of Aristotle versus Galileo? Okay, so we've all heard the story of Galileo dropping, 2 spheres from the Tower of Pisa, one made of, I don't know, something heavy and one made of something light, and then falling at the same rate and touching the ground at the same time. All right, this is probably a fiction. That's not how he discovered this, probably. So we started thinking about, actually, the way that he probably discovered this, if you read about this, he was sitting in church, and he was bored to tears, and he was looking at this clock swinging, just trying to figure out how many more swings of the clock he'd be in here, and he realized that there was kind of this universal relationship between frequency and length, and it didn't matter what the mass was, right? It's a relationship between the length and this universal constant of gravity. And so he actually developed these extremely intricate ramps in still rooms where he had these little bells, so you could actually measure distance by time. Really interesting experiment. So this is where he actually distilled the universal gravitational kind of idea. But we did this thought experiment, and we actually started doing real experiments with collaborators where we have data of different balls being dropped off of a 5-story parking garage. We have like literally position measurements in time of 13 balls of different density being dropped. And we're not trying to be really, really careful here, and some of them are basketballs, some of them are bowling balls, some of them are baseballs. We took that and we ran it through some machine learning algorithms. And what we find is that we don't at all get Galileo's model of a universal gravitational constant. We find that the rate of fall is proportional to the mass. Because that is what's in the data. That is the Aristotelian model. And again, 1,000+ years to turn this over, because the data doesn't support Galileo's model. It takes a conceptual leap. You have to somehow fundamentally step away from your data and make a conceptual leap to get to Galileo. Okay, the data, if I throw a ball, obviously if I throw a beach ball, it's not going to go as far because it's big and light. Because of wind resistance, because of extra physics, extra discrepancies that are really, really hard to model. Okay, so this is just a point you have to be careful when you're doing these models. The third, oh yeah.
Is it not because the amount of data that you give to your system and also the type of data do not keep actually the information or find information through your data?
So I could build an extremely accurate model of how balls move through the air if I had enough data. But if I used the neural network, I would never come up with a constant gravity. That's maybe our point, is that like the simple answer, like machine learning is not typically built to promote parsimonious solutions, the simple solutions. Usually we get into this realm of overfitting and doing Fourier transforms and making things far too complicated because that's what fits the data the best. So the last kind of vignette is about Kepler and Newton. This is one we've been thinking about for a really long time. I mean, Kepler, based on the vast amount of data from Tycho Brahe, revolutionized our model of the solar system. So he was the one that finally broke kind of this Ptolemaic system, even though it wasn't as accurate, by figuring out that these planets move in ellipses around the sun. Okay, that's a really, really good model. Again, I actually think that machine learning would give you something much more like the Keplerian model, but not the Newtonian model. Okay, so we observe these planets in some kind of a steady state on ellipses. That doesn't tell you what would happen if you tried to launch a rocket from one planet to another. That's a transient. That's an extrapolation. Okay, so most machine learning models, like the best you can hope for is something like Kepler, which would model the steady state attractor and interpolate what you've seen. But extrapolating these transients, that's what we want. Okay, and that's kind of the cutting edge of research in this field, is trying to go from Kepler to Newton, trying to go from Aristotle to Galileo. Okay, that's really what matters for us as physicists. It's not that 0.1% extra accuracy that you can get from a deeper neural network. It's some kind of a parsimonious solution or some kind of a generalizable solution that actually allows you to extrapolate to new regimes. Okay, that's all I have for now. I'd be happy to answer some questions. And after the coffee break, I'll talk about how to use some of this for machine learning.
Question?
Yes. At some point in your talk, you mentioned that the difference between a neural network and a brain was the body. But the robot that you had falling early in your talk had a body.
The what?
The robot. I mean, this robot.
Yeah, the robot does have a body.
And had an interest in not falling.
No, I mean, this is almost a science fiction idea that, I mean, the robot, imagine 100 years from now, we have robots with artificial intelligence. They'll probably be much smarter than us, but their bodies will still be, I think, not nearly as rich in terms of sensory modalities and function. And so, yes, we have robots. Yes, they have sensors. They don't have the type of sensing and feeling and kind of interaction that we have. They're still fundamentally limited by their bodies.
As a mechanical engineer, I think that it's much easier to build a body than to build a brain.
I disagree completely. I think there are unique challenges in both. I don't think building a body, I think that's massively oversimplifying how kind of exquisite our mechanical sensory systems really are.
Okay.
One here or one there? Yeah, maybe start there. Yeah.
Recurrent neural networks.
Yeah.
So, do you see that the possibilities to adapt it to learn from a high fidelity CFD simulation, for example? Is it computationally efficient to use this kind of temporal data for RNNs?
People are trying really hard in dozens of labs and making various degrees of progress. So I've seen a lot of examples where it's not obvious why we're doing it and what the benefit. So did everyone hear the question? Can we take a high fidelity CFD solution and learn kind of a neural network model to step this forward? The answer is definitely yes in some cases. In some cases there's a benefit, in others there's not. There's a really nice work by Michael Brenner and some of the Google folks who have shown that with some modern machine learning architectures, you can simulate systems with shock waves much more accurately and efficiently than you could with computational schemes. And essentially, it's like learning computational stencils that are better and higher order than what we have right now, things like that. I would say that it really boils down to how clever the group is in formulating the objective and tying that to an architecture. The really good ones are able to do it. I think it's not obvious how to do it, though. Yeah. Oh, yeah.
Yeah, I'm sorry. I would like to come back actually to the example from just before. For the gravity, for example, when you speak about the ball that you throw, could it be that just because, speaking about the quality of your data, we are all subjected to the same gravity? So if you would have some sample that you could give to feed to your neuronal network of the same ball but on the moon or something like this, well, then you would be able then to, as you said, to interpolate, not extrapolate, but interpolate thanks to the new information that you get from your data.
Yeah, that's absolutely a great point. So this whole history of science is something Nathan Kutz and I spend a lot of time kind of talking about together, and I think he was the one who found this in Principia, I think in book 2. Are these accounts of Newton doing these painstaking experiments where he has balls on the end of pendula in different fluids of different densities, so that he can start to disambiguate the effective fluid resistance from the gravitational effects. Because even then, they still had these debates about, was gravity constant? Were these motions consistent with the data? And so, in lieu of going to another planet, he created a different atmosphere for his experiments. And so you absolutely need that kind of richness of data to make these hypotheses. Yeah.
So you have made a very good point that with machine learning, you can only do interpolation and not extrapolation. And you need a lot of data to fit a complex model. And I would say that most of the the fluid mechanics problems have only sparse data. Let's take the talk of Stefan Goertz on Friday. So he will talk about an Airbus, and the Airbus has different. You want to know the flow at different Reynolds numbers, at different Mach numbers, at different ground heights, at different angles of attack, and so on and so on. And if you look how much data you would need in order to fit your mapping x to x dot, it's impossible. Yep. And now the next thing, and I could give many of these examples, I would argue that most of the fluid mechanics problems will never generate, or let's take the actuators. At some point we talk about flow control. Will we ever learn where we need to place which type of actuator with what amplitude range, frequency range, location, and so on? We need to have the most effective flow control. Now we need millions of experience in order to guide us and in order to do the interpolation.
So this is such an important point, and I mean, we'll talk more about this in the next segment. But I hope everyone is paying attention. This is critical. The quality and quantity of data we have in fluids is fundamentally different than the quality and quantity of data Google has for images. Okay, we are data rich in some dimensions. In fact, we have too much data, right? You run a simulation. I literally have people physically mailing me hard drives because they have so much data and we want to transfer it for one Reynolds number, for one Mach number, right? So we're data poor in the dimensions we care about, where we want to know what's the effective Reynolds number, what's the effective geometry. Those are expensive to get data that's rich in those dimensions. And so this is a fundamental problem that we have that we're still wrestling with. We're still figuring this out. And I think, Barrett and I have talked about this, kind of what is the extrapolation, what is the data set we need in fluids that would be like the ImageNet data set for fluids. And it's bigger. I won't spoil it for you, but it's bigger, and it's a lot bigger. Okay, we probably want coffee. All right.
Then, thank you.